This is the last topic of the semester. Just a reminder, finals week is next week. So the final will be in 2 parts. The first part will cover units 1 and 2. The second part will cover units 3 and just some follow-up questions about the semester. Monday and Tuesday is part 1. And Wednesday and Thursday is part 2. And remember, you are allowed all of your notes. You're allowed everything I put on Canvas for you, except that NetTutor. You can ask me for help if you get stuck. Each part of the final will feel like a regular test. So it's basically you've got 2 tests to take next week. They combine to be 1 final exam. Okay, because I know your time is more difficult and complicated with children and people you're taking care of and work, and everything is chaotic right now. So I didn't want to have you sit down for that long period of time, which is why I broke it up into 2 parts. They'll both be the size of a regular test. I've given you a little bit of extra time, though. I've written them so that most of you will be able to finish in about an hour and a half, maybe 2 hours. So I'm actually giving you 2.5 hours for each part of the test. So I've given you a little bit of extra time just because it's the end of the semester. The stress levels are high. There's more to it. There should not be any surprises on either parts of the final. Hopefully you've noticed that the practice test tends to be very similar to the actual test. And remember, you can always text me if you get stuck. If the pictures aren't showing up, try a new browser. That usually fixes most of the problems. And honestly, that's why I suggest just start the test on Google Chrome, or at least if you're not using Google Chrome, log in and check to make sure you can see all the graphics. And if not, then log into Google Chrome. Also, just a reminder, the class ends next Thursday at 11:59 p.m. That is the last time you can submit any materials for this class. So there will be no extensions on that second half of the final exam. I'll happy to give you extensions for the first part or any other assignments, but everything is due next week, Thursday at 11:59 p.m. Whatever you want to turn in late, I accept everything late up until that point. If anybody wants to take either of those tests early, just tell me and I will open it up early for you. The next class period, we will be reviewing Unit 3 and giving you an overview reminder of what's happening or what happened in Unit 3. You have information for Units 1 and 2 because you had tests in Units 1 and 2, so you've already had a review on those things, which is why I'm starting with Unit 3. That said, bring any questions you have on any topic and we'll get them answered. We will push forward. In Lesson 23, what we're looking at is 2 different things, and they're both different versions of what's called a chi-squared test. So there's 2 different kinds of chi-square tests. Chi is the Greek X. Okay, and so these chi-square tests behave like any other kind of hypothesis test, except they're both specific to a certain scenario. And hopefully you've noticed that in lessons 19, 20, and 21 and 22, we had different scenarios happening. In lessons 23, we have 2 more different scenarios happening, and they're really unrelated. Okay, the first part of lesson 23 is looking to see if a sample that we get is representative of the population. That part isn't new. What's new is in this scenario, our population is really more of a distribution of things, right? So if I'm going to start with an example that will hopefully make it a little bit intuitive. Let's think about M&Ms. This is where it's disappointing that we're not in person, because were we in person, every single one of you would be getting your own bag of M&Ms. So we could all do this together. And it's a lot of fun because then we get to eat the M&Ms at the end. And who doesn't love M&Ms? Okay, I understand. Some people don't love M&Ms. M&Ms, think about when you get a bag of M&Ms. If you were to pour that bag of M&Ms out onto the plate, would we all get the same distribution of colors in our bag of M&Ms? No, and you know that by now. We've done enough of sampling to know every single sample is different. Although M&M Company did release the proportion of colors in their bagging process, and they released that a number of years ago, and statistics teachers went nuts because it's such a widely used example of M&Ms and the distribution of usually blue M&Ms within a bag of M&Ms. And so once M&M's released this, it was, oh my God, it was crazy. And if you just Google M&M color distribution, you will see a slew of blog posts and worksheets and I mean, like proper papers published. I mean, people lost their minds. It was crazy. But since then, a couple years ago, M&M removed that distribution off of their website, leading people to think that they changed their distribution again. Because why else would you remove it? If not to say like, because it's already out there. Once it's out there, it's out there. The internet knows it. So why would you remove it if you didn't change the distribution? So there's a little bit of conspiracy theory stuff happening here. So I happen to have a little bit of M&Ms left over from my big old thing. I mix this with mixed nuts. It's very delicious. My own little gorp. So I've got my package of M&Ms. So here is my plate of M&Ms. Okay. And someone asked me yesterday, did I eat all the red ones? No, I did not. I don't pick out different colors. This is what it looked like. Okay. And by the way, this double one over here, you see, that double blue one, I'm counting that as one M&M. So those are all my M&Ms. What we have here is we are going to compare my sample of 88 M&Ms, here's the color breakdown, versus the proportion of colors that M&M or said they had in their bagging process. So we're going to compare what I've got with this proportion here to see if it does look like the proportion has changed. We know proportions differ for each sample. The question is this distribution different enough from what it's supposed to be that I can say the proportion has changed, or is it just a factor of the sample and it's only off by a little bit, not statistically significant? It may not be off enough for us to warrant saying, no, it's definitely changed. I've got my frequency. This is also a good reminder for the final, because this frequency table is going back to unit 1. We did this, and then expected value. That's what this number expected. This is expected value. That goes back to unit 2. My frequency, I can figure out this relative frequency. There's 88 M&Ms total. So the relative frequency is 6 out of 88, 17 out of 88, 23 out of 88, etc. Okay, so we can figure out those proportions. This is 0.07, 0.19, 26, 18, 19, 22, or 7%, 19%, 26%, 18%, 19%, and 22%. Okay, so you see, like some of these are pretty close to what they should be. The orange is 19 versus 20. We don't expect that to be much. These are pretty similar too. A couple of these are pretty similar, but then you go down to here to brown, especially brown and red. If you look at brown and red, those are really different. Yeah, it might be that they've just changed the brown and the red distributions. Okay, we don't know. Like the hypothesis test that we did for lesson 22 with the ANOVA, hopefully you remember that when we have more than 2 categories, all we can say with this hypothesis test is not how these proportions have changed in relation to each other, because there are too many options for that. What we can say is either they are as expected and it's not statistically significant, or these proportions has changed. Okay, so either there is evidence that these proportions have changed, or there isn't enough evidence to say these proportions have changed. So that's our null versus alternate hypothesis. Okay, so I have this here, my null hypothesis, and don't worry, I will post this on Canvas with the notes. So my null hypothesis is that the proportions are as the same that M&M said. Okay, my alternate hypothesis is going to be very similar to what we did in lesson 23 with that ANOVA, and that is going to be the proportions are different. And this bit here is the same for every test. And so what we call this test is a goodness of fit test. We call this a goodness of fit test, and you'll see this here, goodness of fit, because I've got this proportion here. We never expect our sample to have the same exact proportion, but it could be close enough that we call it good. And that's why it's called goodness of fit. Does my sample fit reasonably well within our expected proportions? What I need to do is I need to figure out these expected values. And remember, Expected value means if things look like this, if I got these same exact proportions, how many of each color would I expect to get in my sample? When we're talking about these, it's just n times p, the number in my sample times the probability of getting that specific color. Okay, so these are all going to be 88 times whatever proportion is here. Okay, so and remember, when we're doing calculations, we have to translate that proportion to a decimal. So 88 times 0.13, 88 times 0.2, 24, 6, 14, 13. Okay, so my proportions, my expected values are 11, 18, 21, 14, 12, and 11. Okay, so you can compare this to that. Okay, you might want to take a screenshot of this so you remember what it is we're looking at. Okay, now what we're going to do is we're going to put all this in our calculator. If you don't have the function that we're about to use, the instructions for you are on the top of page 2. The Goodness of Fit test was a late addition to the TI graphing calculator family. Okay, so if you have the TI-83 or one of the very early 84s, your calculator will not have this function and you have to do it all manually. First thing we need to do is we're going to put our raw data, our observed frequency of each color into L1 and our expected frequency into L2. So go to stat. So we're going to go to stat. Just as a shortcut, you see number 4 is clear list. We're going to clear all the lists. You need to tell it which lists to clear. We're going to clear L1, and remember that second one, and then comma, have it clear L2, second 2, comma, L3, comma, L4. Okay, we're going to need all 4 of these for the second half of class, so let's just clear all 4 right now and press enter. And then if you go to your lists, they should be empty. So go to stat, edit, and you see all my lists are empty now. Does anyone need help with their calculator? Okay, so in L1, we're going to put our observed values. So observed means whatever was in your sample. 6, 17, 23, 16, 17, and 19. Okay, I'm going to check to make sure there's 6 of them. Yes, I have 6 colors. Now go to L2. It's very important that both of these lists are in the same order. 11, 18, 21, 14, 12, 11. So there's our expected values. Double check these lists are the same size. They are. Okay, so it's those little things that can make a huge difference in how many problems you have later down the road when you try to do the calculations. So now what we're going to do is press stat, go over to to tests, go over to tests, and we're going to arrow up. And we're looking for D, chi-square GOF test for Goodness of Fit test. So now you see it's asking for your observed and expected values. It should default to L1 and L2. Always double check that this is the correct one. If you swap these, then that's fine. You just correct it. Remember, second 1 gives you L1, second 2 gives you L2. Now this DF, we haven't talked about this yet. Degrees of freedom is however many categories you have minus 1. Okay, so how many M&M colors do we have? 6. 6 minus 1 is 5. So we have 5 degrees of freedom. Degrees of freedom is categories. Doesn't matter how many items you have, it's all how many possible options are there. So we're going to go down to, I'm going to do draw because I think it's cool to see the curve. There is our chi-square curve. This is, you see, it's not a normal curve. I'm sure most of you know that that's a skewed. Pop quiz, is that a right skew or a left skew? Yes, awesome. Good job. Yes, right skew, because remember that skewness is talking about where it gradually goes down. Okay, it's where that gradual slope is. It's a right skew. Okay, so now you see I have my chi-square test statistic. Again, we're not focusing on this, but it does behave very similarly to a z-score. And then here we have our p-value. And remember, our p-value is the probability of getting a sample that looks like mine if those proportions hold true. Okay, so write those values down.
I have a question about the drawing on the calculator. So whenever I try to click like draw for the thing, it says like error.
Okay, so go back to, see up here, remember stat plot? Go to second, y equals for stat plot. And if you're getting an error, the easiest thing to do is just to turn all the plots off, and that's number 4, and then enter. Most often that's where the error is occurring. Now go back to the stat tests up to the goodness of fit test and press enter, and hopefully you'll be able to get the draw this time.
Okay, yeah, I got it that time.
Okay, good.
Yeah.
Okay, and I did not tell you what the number to beat is. If you are getting that error, if you're on the test or something, or it's 2:00 in the morning and you just need to get it done, just go to calculate. Okay, and you see here we have that same information. Okay, the CNTRB, don't worry about that. That's beyond the scope of what we're doing for this class. Now, I did not tell you what alpha was, level of significance is. So what do we default to? 5% or 0.05. We got a 0.0575. Which number is bigger, P or alpha? Okay, so the P is bigger, yeah? But here's the thing. Look at this. Look at how close they are. That isn't that much bigger. So here is where we would have an argument. I had the same thing happen with me with my grad school, right? So I'll tell you that in a moment. So technically speaking, yes, P is bigger. And this is why in all of the examples you were doing on the homework and the tests are very clearly bigger. Like this is relatively close. If we were just to stop reading here, those are the same exact number, aren't they? So what do we do when it's equal or when it's really close? And this is where we get into some arguments, actually. So technically P is bigger. So let's go with the technical rule for now. Okay, we're going to do technically. Yes, P is bigger. Are we going to reject the null hypothesis? Remember the saying, if the P is low, that hoe's got to go. So P is bigger, so the P ain't low. It's got to be lower than that level of significance. So we're not going to reject it. I'm not saying there is not enough evidence to support the alternative, because strictly speaking, P is bigger. P would need to be less than 0.05. That said, I do want to say this. Those are really close together. Okay, why all of a sudden is 0.05 or 5.75% is now too big, but if we had like 4.9%, that would be small enough. That little minuscule difference is the difference between a yes or a no switch. That 5% is completely arbitrary, totally arbitrary for why it's become the default standard. If you go to conferences, people legit will argue, like full on argue about why we would reject it when it's so close. Like serious arguments. And I even had the same argument when I was in my doctoral program. I had these really powerful results, and I had this type of significance level. And my advisor was like, no, you've got to reject it because it's more than 0.05. I was like, but just barely. And he's like, nope. So just because of him being one of those hardcore steadfast, it's got to be the 0.05 or I can suck it. These amazing results I got thrown out the window and were completely ignored. And they told a really important part of the story I wanted to say, but I wanted to finish my degree. So I was like, okay, fine, you can have it. I'm not willing to die on this hill. I just need to get this degree done because I was already a year over. That 5% is completely arbitrary, and that's a really important thing to understand. If we had said 0.06%, we would reject that null hypothesis. So just know that's the importance of that level of significance, is people choose it arbitrarily but feel very strongly about their choice. But it is still arbitrary. I have a colleague, a friend of mine. I don't know if I've told you about him. We went to SF State together, transferred from Laney together, and he got his bachelor's degree in statistics. And he now owns his own company. He's making 6 figures. All he has is a bachelor's degree in statistics. Because when you understand this stuff, people will throw money at you so that they don't have to deal with it. Because that's the level of I don't like math we have in this country. And he is one of those people, he will die on the absurdity of that 5% hill. I've heard him get into some crazy arguments with people about that 5%. For him, that is a hill willing to die on. Okay, but just understand it is completely arbitrary. Does the evidence suggest that M&M's changed its proportions? Maybe. I mean, that 5% technically says no. But really, it's close enough that I go, yeah, maybe. What that tells me, getting that close to that 5%, that tells me we should do another sample. So next time you get some M&Ms, if I could, I would have mailed all of you M&Ms to do your homework with. So you could actually do this on your own, and we would compare the results and see what the trends were. Because the more times you do a sample, the better your information is. If I'd done this whole thing, that we would get a different result even. All right. Okay. So in example 2 here, we're talking about horse racing. Okay. So there's a theory in horse racing. Some people think that what post the horse starts in, affects whether or not you win. If we're looking at the horse race, here's my starting place. Okay, and then they run in this direction. Number 1 here is on the inside, and here we have number 10, which is on the outside. Okay, and the same is true if you run track. Okay, so if you look here, I've got my observed wins. I watched 114 derbies and recorded what post they were in and how many wins came out of that one post. If you look at this distribution, does it look like any one did better or worse than the other? Well, yeah. Doesn't it kind of look like 9 is the worst place to be? Out of 114 derbies, this one did the worst. Right? Pretty consistently. Number 1 did really well too, but 19 versus 14, that to me doesn't say as much. I look at this and I go, wow, 9's terrible. I don't want number 9. All right. So what we're going to do for this one is we are going to compare my observed wins versus what our expected wins are. And our expected wins would be if it was equal across every single post. Remember, post just means starting position. So if all things were equal for these 114 races I watched, they should all have 11.4 wins. Okay, now you might look at that and say, how can you have 0.4 wins? And you're absolutely right. But we're just going to go with that 11.4 because it's statistics, so we get to ignore those little anomalies. If you get an error, try it with just the 11, not this 0.4. I would like you to answer this question of, based on these results, should the bettors consider the post position? And remember, that just means starting position. Okay, welcome back. So you should have the null hypothesis being that every position has the same probability, or that is p equals 0.10, and that the alternate hypothesis is that at least one of them is different. Remember, when we have more than 2 categories, we can't say how things are different beyond just saying that one of them is different. That's as close as we can get. If we want to know specifics, is one less, is one more, we wait and see what this turns out to do. And if we do wind up rejecting the null and going with the alternate hypothesis, we would then need to run another test to determine how things are different. Okay, so this test is strictly just to determine, are they the same or are they different? Also want to make sure you know that you don't have to put observed into L1 and expected into L2. That's that screen where if you have them in different categories, all you would need to do is just tell your calculator that by switching L2 and L1, for instance, is most often you'll have expected in L1 and observed in L2, and just tell your calculator where to look for those. The evidence is our observed wins, and basically we're just putting those into the calculator. That's step 2 for this goodness of fit test is pretty easy. Degrees of freedom, remember, is the number of categories you have minus 1. So we had 9 degrees of freedom. The most common place to get errors in this is for this 9 degrees of freedom not matching the 10 pieces of data. Okay, if I have 10 pieces of data and I put, let's say, a 10 for degrees of freedom, the calculator will give you an error because it's going to look at this versus this and compare them. You should have got p equals 0.154, and our alpha then is our level of significance is 0.05. So the question is, are we going to reject the hoe? We are not rejecting the hoe. And that is because in this example, our P is bigger. So the P ain't low, so the hoe don't go. Because we are not rejecting the hoe, that means there is not enough evidence. Okay, and remember, these two always go together. If we're not rejecting, there is not enough evidence. Let's move on to the second half of this lesson 23, this other chi-squared test. Again, it's still a hypothesis test that we're doing. But now what we're looking at is we're using this chi-square hypothesis test to determine if two things are independent of each other. And you may remember in lesson 11 is when we initially talked about independent and dependent variables. And that was an example of is having children related to whether or not a parent works from home? Okay, is working from home independent of having children? In order to figure that out, what we had done originally is we had looked at those conditional probabilities. The problem with the conditional probabilities and using that is we had three categories of kids, none, one, or two or more, if I recall correctly. And we had three categories of parents. We had both parents work from home, one parent works from home, or no parents work from home, right? So in order to do the probabilities, those conditional probabilities, we would need to do it a bunch of different times to see if each individual category was independent of each of those other categories. And I don't know about you, that's a lot of work, right? We like to be efficient when it comes to doing statistics. The conditional probabilities are great when you have exactly two categories and you want to know, and only two categories, and you want to know if they are independent of each other. When we have that situation of multiple categories of parents, multiple categories of children, and we want to determine if those are independent or not, the easiest and most efficient way to determine that is to use a chi-square test. And so with the chi-square test, the null and alternative hypothesis are going to be the same every time. And it's called the chi-square test for independence because we're using the chi-square test to determine if things are independent. The null and alternate are always going to be the same. Two things are independent of each other is going to be our null hypothesis. And our alternate hypothesis is always going to be that these two things are dependent on each other. For this first example, what you were asked to look at is whether or not someone's age was dependent on whether or not they're more likely to buy American-made goods. I'm going to, again, honor the work that people had done in the pre-class assignment. And so I'm going to skip that example, and we're going to go to example 4. And in example 4, what we're looking at is whether or not being married is dependent to your happiness level. Completely made up statistics. I just want to make sure we're clear on that. Okay. This isn't based on any real data. This is just me making stuff up. Let's look at example 4. We have this two-way table, and we want to know, does this sample evidence suggest that one's happiness depends on marital status? And we're going to use a 5% level of significance. That tells us alpha equals 0.05. We're going to write our null and alternate hypothesis. And again, these are basically going to be the same for everything. All we're going to do is include one's happiness and marital status. Essentially, we're using this sentence right here and just rephrasing it. So for the null hypothesis, I would write that marital status and happiness are completely unrelated to each other. And really, in other words, that means, i.e., they're independent. Then my alternate hypothesis is going to be that one's happiness depends on marital status. And you might recognize that phrase because it is right here. And that is to say they're dependent. Okay, and you might remember, since we're here, I'll just remind you that when we were doing this in lesson 11, how we would have had to figure that out is the probability of A would have to equal the probability of A given B to be independent. And that is to say the probability of marital status out of everybody would equal the probability of marital status based on their happiness. So that is to say changing the denominator would not change the outcome of the probability, because this probability, remember, is out of all the people in the table, but this probability is just with the denominator of B, okay? But we're going to use our calculator to do it. This one is more complicated. What we need to do is we need to put this table into our calculator. So we're going to use a matrix, and I'm sure some of you are familiar with a matrix. There's a lot of high school math classes that might use a matrix. We're going to put all this whole thing just like this. We're going to replicate this in our calculator. So second x to the minus 1, where it says matrix, you don't worry about the names. Okay, we want to go over to edit because we want to put our data in there. We're going to use A. We're going to press enter. And now you see here there's just one box. We need a much bigger box. So this is rows by columns. So I have 3 rows, and then arrow over to tell it I have 4 columns, and then arrow down. And you see now I've got my 3 by 4 that I can replicate this information. And it's going to work across, so I'm going to put in the first row. And make sure you press enter after this very last one, otherwise it won't take it as an input.
The fourth entry on the first row is 144, not 114.
Oh, thank you. Now we're going to have it crunch these numbers. So we're going to go back to stat and go over to tests and arrow up. And you'll see we're using now this other chi-square test. Okay, and test means, we're doing a hypothesis test. So this is just a regular chi-square hypothesis test. So press enter. The observed, this is where we use that name. We're telling the calculator our observed values are in matrix A. Now expected, just leave that as it be, because what it's going to do is it's going to create another matrix to do a whole bunch of calculations. And then we'll go to draw, and there's our chi-square curve, and there's our probability. You see our test statistic? Remember, this behaves like a z-score as 224, and our probability is 0. If we go back, look at the calculate option, press enter, and you see this is why it gave us a 0, because our true p-value is 1.3788 times e to the negative 45. That is a decimal point, 44 zeros, and a 13788. That's ridiculously small. So that's where we remember say effectively 0. And just since we're here, I'll show you. It calculated the degrees of freedom for us as well. The degrees of freedom isn't difficult to calculate, but the calculator does it for us, so we don't have to worry about that. That p-value is effectively 0. Are we going to reject the hoe? Remember, if the p is low, that hoe's got to go. Our p-value was 0. Our level of significance is 5. Our p is smaller than our level of significance. Okay, so this was effectively 0. So our alpha is bigger, so the p is low, so the hoe's got to go, which means that we are going to reject that null hypothesis, which means there is enough evidence to support the alternative. So remember what we were actually doing. Does one's happiness depend on marital status? So in this context, we're going with this one. One's happiness does depend on marital status. Okay, so there is evidence to suggest the happiness depends on marital status. And remember, we're not trying to say which status makes you the happiest. We're just saying that there is a relationship there. And example 3 is also a 3 by 4 matrix. So you can just go into example 3 and just write over that information you have there if you haven't done example 3 yet. Okay, it's the same size of matrix. Mm-hmm.
Wondering if we could just go over a trick for knowing which one to use, because that's always what I get confused on.
Yes. Okay. So the test for independence will have a two-way table, and the goodness of fit will have proportions. Okay, in both of these, notice there's more than 2 pieces of information. That's another clue. For lessons 18, 19, 20, and 21, those all had 2 options. There were either one sample and what had happened in the past, or there were 2 samples with only one category in each of those samples. In lessons 22 and 23, you've got multiple categories and multiple samples happening. With that, we are finished. That is everything. Give yourself a round of applause and a pat on the back. You did it. You're still here. Congratulations. Congratulations. I'm certainly very proud of all of you for making it this far. Congratulations. It's been a crazy way to start college or even just take a math class. It's a crazy way to teach. It's a crazy way to learn, but you made it. Okay, I know you have learned a lot this semester, and I hope you recognize that you did too. So congratulations. You got your math class done. You should be very proud of yourself. I'm proud of you. Take it easy, everybody.